is or not here. So upon reset, we want to change the output to 0, right? And we're saying that each clock event, the event is just looking for either the rising or the falling edge whenever there's a transition. And in this case, we are using if clock event and clock equals 1. Then we want the Q to be equal to what? D. We want the output to be equal to the input. Yes? So if I've compiled this, hopefully I did, just open my software. Let's see. File, open project, then flip-flop, let's see, open. Yep, we have the project open. So anyway, debugging stuff, this is for you. If you don't see this in this, you probably don't need the VHDL file. So let's see, let's try to run the simulation. On verification, you go to the university program and you double click there. Node finder, list, move all of them. Okay, and another okay. I'm not interested in varying the resets now. Same for, we just want the clock signal. Set it to that, and we want to vary this all the time. Yes, maybe we do. So let's set it to vary every 20 milliseconds, and then press OK. So if I run this simulation and we're lucky, waveform, I have one there already. Those who miss class altogether, do we sort of feel that we understand what a VHDL code is about? Yes, no, maybe? No. Yes, no. Did you understand what I did over there? Yes, no? Smile, yes. But you don't feel comfortable.
It's an error.
Huh, interesting. Let's see what happens. What did I do wrong or what did I do right? And so what we noticed with the latch is that the state was changing here, right, on the stable point. So you can't have the output, as long as the enable is 1, you can't, or the clock, you can't have the output also changing, mimicking exactly the same timing as this one. That's your latch. If it's a flip-flop, just because we put clock slash event, right? And that's our data. Let's make this our clock. And what we were, the same structure. Can I clean it? Yes, thank you. Okay, so, on. We have this being our D and that being our clock, right? If we are looking at a flip-flop, it's going to look only for the rising edge. Flip-flop design our way with the rising edge. It's going to look only for the rising edge of the clock. So in here, the rising edge of the clock, the value becomes equals to D. Then it will say, right, rising edge of the clock, D is 0, then it will fall. So the timing is going to be exactly on the rising edge. But for the latch, in this particular case, if there was a change in D, it would change at that point. If it's a flip-flop and then D became 0, it will not change. Good? Now, the reason why I'm taking my time to go through this is that you look at a waveform, you analyze what is happening, you look at your truth table, or you look at your circuit diagram, is that what you wanted to create? You make your comments on the waveform. You can actually circle stuff on there, put 1, 0, which is easy actually to do in the proper notebook book. But anyway, this you can work in software, you guys will figure it out and do amazing stuff with it. Then you actually comment on it. Does it behave exactly the way that you wanted it to behave? Can you compare one design to another? Those are the kind of things that fetch you mark, because that shows that you've done it yourself. Yes? And by the way, you should be prepared to either go with the class right now in terms of the learning curve, or later be willing to give me a full demo. And I've said demo means I'll delete certain parts of your code, I'll ask you what will happen and you fix it yourself. So it's actually better now that we're actually all picking up from the same page. It's better to work with us together, or even ahead of the class. You have all the resources for it. Good. Don't need to simulate this. I'll look at the simulation by shooting. Do you understand me so far? Yeah? 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 Okay. You understand me so far? Yes? No? Maybe? Somehow? Good. All right. You understand me so far? Yes? No? Maybe? Somehow? Maybe? Completely lost. Can't figure it out on your own if you go home and you read even the code, or I give you the code and watch the video. No, it doesn't mean you can't learn it, but it's just, I've completely lost you. Let me know now. Maybe means you can follow the lecture as I continue. Or you have a question, ask now. I'm not going to ask for the 4th time, I've like 3 times now. Can I carry on? Yeah? Okay, good. Actually, I've brought coffee, so it means we're going to go fast paced at some point, but I'll slow down whenever I have to. Signals. When we use signals? Say something.
Right now, there's one thinking that when the electrical power goes to the gate.
Sorry?
When the electrical power goes to the gate, the side monitors.
Signals.
Is the clock?
So far we have when the electric power goes to the gate. When we use the signal keyword, and where do we use it?
The signal is on the logic gate.
On the logic gates, you mean the internal connections within the chip itself? Yes?
Yeah.
Inside the architecture, okay. Is it before or after the begin?
Before.
Before the begin. Good. We all happy people. Right, okay. Wonderful. Now, there are 2 ways that we can define internal wires. We've been using signals so far. It's not advanced. Right? We've been using signals, right? You can also use variables. Now, variable, we are all very familiar with variables, yes? Yes. So, you can define, now we are just inside the architecture. So, architecture, blah, blah, blah. You have your signal. Your signal can either be a bit, just now we just changed a bit to a logic vector. If you look at the slides, you will see some funny definitions of bits and everything. Don't stick to those ones, they'll give you errors, but just use the ones we've been doing in class. Yeah? If someone struggles so much and spends 24 hours on it, it means the person never came to class, so just let them be until they buy lunch for it. Right. Yeah, good. And he didn't record that. Right, so we can have variables or signals. 2 of them similar job, but completely different. So I change the similar job to similar concept. Good. Right. So within the architecture, when we begin, signal variables, unlike signals, are normally used within the process. When do we use process? When do we use process? See, how you doing?
Sequential.
Sorry.
No, take your time. To create sequential execution, right? Yes, same concept as high-level programming language, yes. By the way, if you hear for the first, the VHDL code is concurrent, right? Which means you can say Michael is here before he actually comes here. Does it make sense? Simply in C++, you can have x equals 1, y equals, I don't know, x plus z, and then you write z equals 2. In C++, or Java, this will give you an error because it's sequential, and it doesn't know choose z before you use z. In VHDL, it will run it for you. Yes? Good. We understand that concept. So process allows sequential execution, right? And variables are mostly used within processes, which means there's something closely coupling variables to sequential execution. Yeah? Cool? No? Maybe I confused you somehow. Right. Signal assignment. You've been using the arrow, right?
Yes.
Similar, the variables is a column and equal sign. Yes? Now, here's the thing. You begin your process, you end the process. The assignment is similar, or the definition of variable stuff and signal is similar. But in terms of the assignment is different. You're assigning a value to it is different in terms of keywords. Now, the variable, the signal values are actually assigned after the process exits. So if we're going through this and we have the signal y equals 0, and y was originally equals 1, this new value, 0, will be assigned after the process exits. So if we are looking at the circuit and we're running it for the first time, on the first clock cycle, the value of the signal will be updated after this block exits once. Make sense? It's tied to the flip-flop design, right? It's assigned after the clock moves from on the event transition, right? Variables or signals are needed to create flip-flop, so we use signals to create flip-flop. And last week I mentioned metastability, right? We all said that brings our turn on, so we go on. Metastability means you can have several states. Did I mention metastability? No, I deleted to repeat it in the beginning. Right, okay, so basically you have simple, I have my phone, he has his phone, we connect the two phones together and then they are communicating, right? The internal clock that my phone operates on, I don't know, let's make it at 5 gigahertz, right? Or 5 megahertz, right? So, and his probably work at 52 megahertz, right? Completely different synchronized world. Yes? But they are communicating and seamlessly. It looks like everything is brilliant, right? But what that means is that at this point, when my data is being transmitted, if my clock is moving from 0 to 1, 0 to 1 at this speed, and his clock, right? And my clock is moving very slow, 0 to 1, 0 to 1. Some points will exist that actually my phone speed is too slow and it can actually try to operate at the points where his phone's speed switching on transistors. Makes sense? So if transistors switched on looks like from 0 to 1, right? But actually it takes time to set up. These points are invalid states. You can call it setup time and all those things. Electrical electronics engineering people know this or should know this, right? Because it's a MOSFET, right? It's actually a physical device, right? So even though we draw this square wave, it's not a perfect square wave. If my phone is trying to transmit data to his phone, which is operating at a different course, actually send data during this transition time. It will be read, a 0 could be read as a 1 could be read as a 0. It's actually an unpredictable state, so we call it metastability. It's not actually properly stable. It's a stable point of several states. Right? Good. Now, to resolve this, right, at the point of communication, they will put one flip-flop, another flip-flop, so the signal is actually delayed. Sync to my internal clock, sync to another my internal clock, then we have a stable point. Yes, no, maybe we understood 3. Okay, 3, 4 people understand. We are happy. If you didn't understand, just put it in the bin and understand that the signals are used to create flip-flops. Yes, the variables are used for sequential execution. Sequential execution, you want to have if-else statements, right? So, if the value of x, variable called x, changes and you need to make a decision on it, you want it to happen immediately. Yes, no, maybe, have I lost you? It's your name. Have I lost you? What's your name again, last but one person?
Iman.
Iman. Were you here last week? Was it your first week? Second week? The second week here. So did I ask your name last week? Have you met? Huh? Name sounds familiar. If I remember your name, then you must have told me somehow. Right, okay. So if you were here and you are running, then that's fine. It means you understand everything already. Do we grasp this concept? So if you do a lot of reading and stuff, people will discourage you from using variables. Most people would do. But, you know, very common thing. We talk about the program counter, right? And we say program counter continuously, well, points to be located, the next instruction to be executed in memory location, or from memory location, right? The program counter has a counter attached to it, program counter, right? So each time it implements something. So implementing of count variables, was the counters as variables or implemented as variables, right? Now we all understand the code structure of a VHDL code. Yes, no, maybe. Messi is with us. Messi, right? You understand so far-ish? Have I confused you completely? Maybe. At least you can follow the class. Yes? Yes, no, maybe. Good. Right. Is there anything unusual about the first 3 lines? Can we all see? Is everybody with me? I know I like a lot of information, but is everybody with me?
Out has a...
Sorry? The libraries, the preprocessor directives, is there anything new? Yes. So the numeric... Okay. They're doing their own thing, but that's fine. The numeric STD allows us to manipulate numbers. Right? Yes? So it allows us to use the natural, sort of the natural variables, but they're not really variables, right? They're signals, right? So the natural one, we can actually have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we need to actually define the order of the pins, right? So we say 0, 2, 5. So you're going to have 0, 2, 5. You can have 5 down to 0 if you want, right? Okay, good, we understand. Brilliant. And this is our entity. At that point, what are we doing? We just simply, we run back and forth, but let's take it. We draw a black box, yes, at the entity point, and then we have one pin as an input, which, to make it easy, we call input clock, right? I clock. And then 2 pins as output, right? One of them being a variable output and one being a signal output. Good, because what we want to actually visualize the differences between variables and signals and how they operate. Okay. Architecture definition, you notice before the beginning, right? Before the beginning, we have all the signal definitions there. Yes? No, maybe. Yes. Can we all see? Lady at the back in the corner, can you tell me your name, please? Yes. Like, sorry? Arifa. And it's like the 3rd time I fast, right? It's recording. You don't mind me asking them to ask? Nobody minds. Right, okay, good. So if Arifa can hear, we can all hear, right? Yes. Unless maybe you don't understand my accent, and tell me and I'll just rephrase stuff. Okay, so signal definition before the begin. Variable definition after the begin. That's not a variable. After the begin, even after the process. Yes? This is just a label.
Which one?
Variable is like a local variable to a function. Local variable to functions are defined within the function. Yes, then if that helps you remember, then good. Okay, right. So, all STD logics, and we have this, I'm calling signal variable done, but it's actually the signal that will be assigned to the variable done signal. Makes sense now? Right. What I have here will be monitoring the variable. Because the variable is local to the process, or it's like a local variable, if you want to view it globally, you assign it to a global variable within the function. This is concept from high-level programming. If we've all done high-level programming before, even electrical electronics is very good, right? Yeah, good. Right. And we want to monitor, we have a count signal and signal done to actually monitor when the count signal is done. It's just a counter but implemented with a signal. Okay, so variable definition 025, so we just counted from 025. And we understand clock event. Yes? We used it to implement flip-flop 2 seconds ago. Another key word of monitoring the rising edge of the clock is actually rising underscore edge. Another key word. But it's slightly different from the clock event. Clock event variable signal equals 1 means it will always change at on the rising edge of the clock. Yes? Clock event signal. So signal event, right? The event is the keyword. Signal event signal equals 0 means what? It will change on the falling edge of the signal. Yes? Good. Now, rising edge means it will always change on the rising edge of the clock. Now, whenever the state of the clock is a don't care, nothing will happen. Don't care means it can be either 1 or 0. It only changes on the rising edge of the clock. And if you write code, you can write the keyword down. When you write your code, you can play with the two of them to see what is happening on both of them, and you have a bit of notes for yourself.
So you said that one changes on the
So
more
you say A event, A equals and A equals 1, meaning the outputs or whatever you assign it to, it will be synchronized to the rising edge of A.
Yeah.
A event and A equals 0, it means it will be synchronized to the falling edge. That's A going to 0, right? But in this case, obviously, we're forcing it only to the rising edge. Yes, no, maybe, carry on. If I've confused you with this one and you understood what we said before we introduced this rising edge stuff, I'm happy for us to continue there. All on the same page? Ish? Okay. Ish. Right. I've got a bit of notes there. Take a snapshot. Right. So we have the signal, and all we want to do implement is a counter. Different from what we did before. We just force the count or initialize the count value to 0. Right? Well, we done. We'll count the value to 0 and this one to 0, and that's STD logic. So that's why you notice the bits, I put them in codes, the numbers not in code. The assignment is almost the same as when you are initializing a signal whilst you define it. It's almost the same as the way that you initialize a variable. It's not the array. Yes, no, maybe? Good. I'm saying these things because when you get errors, you call me, and then some things are displayed to you to figure out. Okay. So we define our variable and we have our count variable there, and the range is almost the same as that one. So the variable, slightly different assignment, and variable count 1. So we look at the actual implementation. Just note if you are doing this by yourself, and instead of variable before begin, if you put it in there, then it gives you an error, or each time variable will be created and initialized to 0 and your resource will not look like what you're looking for. If you listen, great. If you didn't, test it. Right. So definition for the count, the architecture description for the count using signal, you have obviously if the signal equals 5, you just reset it to 0. You just want it to come from 1 to 5. Yes? So if it is 5, sets the signal to the count signal to 0, and also activate the 1. So each time it comes from 0 to 1, then you have the signal done. Yes? Assigned. The same, obviously, otherwise, the signal that equals 0, we understand. The same for the variable, but the difference is that variable assignment use this column, and I'm using a signal to visualize that of the variable signal because we want to see it on the outside of the circuit, right? Outside the process, outside the function, because variables are local variables. Yes, no, maybe somehow. You understand this way. Right. So at the end of everything, signals are internal to the chip. If you want to view it on the output, you just assign it to the output works. Good. And I probably have simulation of this. I've got a picture presented on the page. That will work. That works. We can run the simulation, assign the inputs and everything, or I can simply do this and hopefully we can also receive. Okay. Can we all see? Yeah? Right. So basically all I've done is because it just assign the clock. Basically that's the main input that changes all the time. Yeah, and we are using the clock to implement the counter. And you realize, okay, so this is the signal out, and also you've got the actual signal pin output. So if I count, that's making it easy. If I count, you have 1, 2, 3, 4, 5. Immediately the signal changes. The variable changes. Let me do something better. Let's simulate it ourselves before. Sorry, that thing was making me do that. Much better. So you've got 1, 2, 3, 4, 5. On the fifth count, the variable changes immediately, right? But the signal wastes 1 clock cycle just for the process.